Hi, welcome to the course on impact evaluation methods. I'm Paul Gertler from the University of California, and today I'd like to start the lectures. There are a number of resources that you can use, all linked online. Here are three of them. One is through the World Bank, which refers to a book, Impact Evaluation in Practice. Another is from the Inter-American Development Bank, and that's their evaluation hub. And finally, our homepage at SIGA at Berkeley. You can get additional resources there, which will help enrich what we hope to learn from these sessions. Today I'm going to talk about causal inference. Our agenda today is what is an impact evaluation, the central role of counterfactuals in terms of implementing an impact evaluation, and then we'll look at two false counterfactuals, or counterfeit counterfactuals. Counterfactuals we all love to hate. One is pre-post comparison, and the other is ex-post self-selected, where we compare apples and oranges. Let's start with what is an impact evaluation. Normally, when we begin an evaluation, we think of a development question. We're interested in how we might reduce youth unemployment, or increase school enrollment, or reduce vehicle transit time. In each of these questions, we propose a solution. For example, we'd like to know if we implement technical vocational training for youth, would that reduce youth unemployment? Or school scholarships to raise school enrollment? Or finally, increasing road quality or road improvement programs to reduce vehicle transit time. At the end of the day, impact evaluation is all about answering the questions, did the program have an impact? And if it did, what was the size of that impact? So we translate the previous slide into a series of research questions. Did the technical vocational research trainings reduce youth unemployment? Did the school scholarship change school enrollment? Did the road improvement reduce vehicle transit time? Impact evaluation measures the cause and effect relationship between the intervention and the result. And what we're interested in is how much of the change in outcome can be attributed to the program and policy versus other explanations. Public policy is based on a theory of change. It's a story which relates the intervention to the results of interest. We'd like to know, is there a plausible mechanism, a plausible series of physical and behavioral responses that would lead the intervention to reasonably be able to improve the outcome of interest. An impact evaluation measures whether or not these results were accomplished. So we use the theory of change to set up and guide the research questions and our measures of success, or our indicators of success. One method of implementing a theory of change is called the results chain. There are many ways to write down a theory of change. A results chain, though, has its uses. One, it's a way of organizing our ideas. And two, many funding agencies like results chains, and so they have to write this down anyway. The way to think about the results chain is in a series of boxes. What we're trying to do might be considered outcomes or impacts, the two columns on the right of the chart. Outcomes are the goals or objectives. What does the program do? Well, the program has a set of activities, and those activities require inputs. Inputs and activities are the two left columns on the chart. Those activities hopefully produce some outputs. By participating in the outputs, we generate outcomes and impacts. For example, inputs might be thought of as the human resources, finances, or other resources mobilized to implement these activities. The activities are tasks and work completed to convert inputs into specific outputs. Outputs are goods and services delivered under control of the implementer. These three activities could be thought of as the implementation of the program or the policy. These are under control of the implementer. Outcomes would be the use of the products by the population of interest, and impacts would be the final objectives or long-term control of the program. These are results. The outputs or activities provide incentives or provide stimulus for either firms, individuals, public agencies like schools or healthcare to respond to those incentives. And impacts are the ultimate result of those changes in behavior. When we think of inputs, examples might be budget, personnel. Activities could be things that are completed to produce the services. Outputs are goods and services produced under control of the executing body. Outcomes are not completely under the control of the executing body. And impacts are affected by multiple external factors. An example might be we're trying to improve school test scores by teacher training. Well, the inputs would be teachers, curriculum, money in order to run training programs for the teachers. The activities are the teacher training programs and all of the necessary work that needs to be put into designing the curriculum. The outputs are the number of teachers who took the training and how well they learned. The outcomes would be the extent to which this teacher training led to improved teaching, increase the quality of teacher-student interaction, and then impacts would be how test scores change as a result of this. Okay, let's turn now from what is an impact evaluation to the key concept in designing an impact evaluation, and that's called a counterfactual. Our objective in an impact evaluation is to estimate the causal effect or impact of an intervention P on some outcome or result of interest, and we'll call that Y. P again is the program or treatment, and Y is the result or measure of success. An example of this might be, what's the impact of a conditional cash transfer program P on household consumption of food, say Y? Now, let's translate the impact evaluation question into a measure. What is the impact of program P on outcome Y? Well, we can display that in the context of this simple equation. Alpha is the impact. Y is the value of the outcome of interest. P equals 1 is having the program. P equals 0 is not having the program. So the impact, alpha, equals the value of the outcome when you have the program minus the value of the outcome when you don't have the program. It's very important that this be measured for the same individual at the same point in time. Impact evaluation or causality is ruling out all other reasons why the outcome might be different when you have the program and when you don't have the program. If we compare the outcome with and without the program for the same individual, there are no differences in income, no differences in educational background, no differences in parental influence. So any characteristic which might be different between individuals is held constant when we compare an individual with and without the program. Also, by doing this comparison at the same point in time, there's no difference in the weather, there's no difference in the economic outcomes, there's no difference in environmental characteristics. We have a problem of missing data. For a program beneficiary, we observe Y conditional on P equals 1, or the consumption of the household participating in the cash transfer program. But we don't observe what the consumption of the household would be if they had not been participating in the cash transfer program at the same time. We only observe outcomes with the program or outcomes without the program at the same point in time. What's the solution? Well, what we need to do is to estimate what would have happened to the outcome in the absence of the program at the same point in time. We call this the counterfactual. The key to a successful impact evaluation is having a good or valid estimate to the counterfactual. And in statistical terms, we want an unbiased estimate of the counterfactual. What would have happened to the outcome, or what would have the outcome have been if the individual firm or government agency had not received the intervention or the program. So, how then do we estimate the impact of the program P on outcome Y? We observe the left hand of the screen, Y conditional on P equals 1. That's the result with the treatment. And we have to estimate the right hand of the screen, what would have been the outcome had P equals 0 not having the program. That's called the counterfactual. We'll estimate the counterfactual by using the outcome of a comparison or control group. So here's an example. We have Mr. Fulanito. We give Mr. Fulanito some cash, and we observe what was the effect of that cash on Fulanito's consumption of caramels. In order to estimate the counterfactual, what would have been Fulanito's candy consumption without the cash, we try and find the perfect clone of Mr. Fulanito. Then we can compare how many caramels Mr. Fulanito eats when he has cash, how many he eats when he doesn't have cash, or how many his clone eats when he doesn't have cash. And then the difference between that, 6 minus 4 equals 2. The reason this works is Fulanito obviously is the same as his clones. There are no differences between Mr. Fulanito, and there are no differences in environmental factors because it's happening at the same point in time. So the only difference between Fulanito having the program and Fulanito not having the program is the program, in this case the cash. So there's no other reason by which those two higher candies would have been consumed except for the cash. We've ruled out all other explanations for the difference except for the program or the intervention. The big problem with the Fulanito example with his clone is there's no perfect clone for every individual. How do we solve that problem? Well, we're going to use statistical properties. Rather than looking at the impact on an individual by trying to find their clone, what we're going to do is we're going to use groups. We have a treatment group here made up of diverse individuals who have red, white, and black hats, and we're going to compare it to a control group made up of people with white, red, and black hats. Now, what we really want is we want these two groups to be on average the same in all characteristics. And by the law of large numbers, if we have two random samples from the same population, the mean of the treatment group and the mean of the control group will be, in expectation, exactly the same. They'll be unbiased estimators of the population mean. And in this sense, on average, the treatment group is the same as the control group before the intervention comes along. So, if we then give the treatment group the cash, and we observe on average they consume 6 caramels, and we compare it to the control group where on average they eat 4 caramels, we find an impact of 6 minus 4 equals 2. We know that on average there are no differences between the treatment and control group except for the cash. Therefore, we can safely interpret the difference of 2 caramels as being caused by the cash. Well, now the question is, we really need to find a way to identify good controls. So how are we going to find these clones for the Fulanitos of our program? Well, we have a set of criteria. We'd like the treatment and control group to have identical characteristics on average, except for the intervention. In practice, we're going to use the program's eligibility criteria to identify good controls. With a good control group, the only reason for differing results then between the treatment and control group is the intervention. Now let's turn to another topic in causal inference. We're going to look at false counterfactuals, the counterfactuals we love to hate. We'll start with pre and post comparisons. So let's return to the question we've been looking at with example throughout this whole talk. What is the impact of cash transfers on consumption, on food consumption per capita, or Y? Well, what we're going to do is we're going to do what is common by many programs, is we're able to observe consumption before and after the program, before and after Fulanito got cash. This is quite common because most programs collect monitoring data on their beneficiaries. They know what the conditions of the beneficiaries are at the beginning of the program, and they update that over time. So it's very easy to turn to existing source of data and see how the outcome changes over time. So in this case, we're going to estimate the impact alpha, which equals food consumption conditional on having the program, minus the counterfactual, what food consumption would have been without the program at the same point in time. But here we're going to use food consumption the year before for the treatment group as an estimate to the counterfactual. So here we're going to look at a particular example. In 2015, we have a per capita food consumption of 233. And that's the horizontal line at 233, which extends all the way to point B. In 2017, that same group has a food consumption A, which is 268 per capita. Then our estimate of impact is the difference between A and B, or 268 minus 233, which alpha equals $35 in this case. Now that assumes that what the food consumption was in 2015 would be the same in 2017 had Fulanito not gotten the cash transfers. What's the problem? The problem is there could have been an economic boom. Incomes may have risen independent of the program. And if Fulanito got more money, his food consumption might have risen from B to C without the cash transfer. And so B would be an underestimate of the counterfactual when the true counterfactual is C. The real impact then is A minus C, and A minus B is an overestimate. Another example is, suppose there was a recession and people's income fell. Well, then their food consumption might have fallen as well, so it went down to point B. In this case, the real impact is A minus D, and we would have underestimated the impact by using A minus B. Pre-post comparisons do not control for other confounding factors that vary over time. The difference between pre and post is driven both by the intervention and other factors such as change in the underlying economy, differences in weather, differences in other public policies. Let's now turn to a second false counterfactual. And this is a problem where we have self-selection, and I might think of it as comparing apples to oranges. The big problem with self-selected groups is we're going to be comparing those who chose to participate to those who chose not to participate, or those who are ineligible with some important exceptions. In general, these selection criteria lead to differences in individual characteristics like income, preferences, motivation, attitudes, family background. And these differences are correlated with the outcome. So the difference between the treatment group and the control group in this case are not only due to the intervention, but also due to these differences in characteristics. We're going to be dealing with an important concept called selection bias. The population's characteristics correlate with the condition under which they participate in the program P and the results of interest. While we can control for observables using statistical methods, primarily multivariate regression, we can't control for unobservables. The impact estimation is confounded by these unobservable characteristics. Remember, pre-post compares the same unit of observation before and after receiving P. The problem is other things can occur throughout time that affect the result. The self-selected compares the group that chose to participate with the group that chooses not to participate. The problem is selection bias. Both of these estimates of the counterfactual can result in biased estimation of the impact.